Yeah, so thank you. Thank you for introducing me. I'm here to tell you about a project that's been going on at the University of Queensland for about 5 years now. And it spans multiple people, nearly half a dozen people, and a few papers. And it's going to be culminating just next week, hopefully, when we upload some of our results to the archive. And our topic is all about character varieties. Now, before I tell you what a character variety is and how we study them, I actually want to do some history, a bit of a history lesson. And I want to tell you about a very old problem. And it's very easy to state, and we'll see later in the talk how it relates to character varieties in the first place. And the problem goes as follows. It's a very easy problem to state. I take two very simple pieces of data. I just take a finite group and I take three innocent looking conjugate classes in my group. And the question is, how many triples are there, X, Y, and Z, whose product is equal to the identity element? Now, of course, if you fix the finite group and you fix the conjugate classes, it's just a finite problem. And so you can put this on a computer, you could solve it by hand, and you could get this number no problem at all. But the real trick to this is figuring out a uniform strategy for finding this number. So for any group, how do we do this? And the answer to this question is basically representation theory of the group G. Now, this is an entire topic that was developed in the late 1800s. And this question actually motivated the representation theory of finite groups. This was one of the motivating problems. Now, I'm not going to lecture you about what the representation theory of finite groups is. If you haven't seen it, it's okay. But a very, very high level, brief introduction to the topic is just I take a group and I create this interesting set of functions, and we call them the characters of the group. And that's what I mean by this chi here. They're just complex valued functions on our group. And I'm not going to tell you exactly how we get them or anything like that, but it's just a finite list of functions associated to our finite group. Now, the only thing I want to talk about these characters is I want to say they have a special property, which is if two elements in the group are conjugate, these characters will take the same complex number on those conjugate elements. And so how do we answer the problem? Well, back in the 1800s, a famous mathematician called George Frobenius said, you have to evaluate this number. So this number, it's a finite sum. We have finitely many functions, and I just evaluate each function on each conjugate class. Now, this isn't the exact number. You have to multiply by the size of the group and the sizes of the conjugate classes, but this is the key value. This is the key non-obvious value that you need to evaluate. And so, as I said, this was the problem that George Frobenius on the right there studied. And I want to take a moment just to talk about some of the history of this problem and what he was thinking about at the time. So he wrote the following paper. I have it on good authority. I don't know German, but Google Translate tells me this paper is called On Group Characters. I don't think you need much of an imagination to figure that out. And you can see it was written in 1896. So this is the paper that founded representation theory, written by Frobenius himself. And I just wanted to point out some things that are happening in the paper. The first thing is the first paragraph, he's talking about the history of a very deep number theoretic problem. He talks about a problem of Dirichlet. He's talking about Dirichlet's theorem on primes in arithmetic progressions. And luckily, it's number theory, so it's actually a very easy problem to state. The problem is just take two primes, P and L, and look at the list of numbers, Px plus L. And Dirichlet proved that this list contains infinitely many primes. And in doing so, he created a very primitive version of a group character. And you can see there those chi-m's and chi's of a's. And on the right there, you see Frobenius's problem of the statement that I just gave you. He's talking about these conjugate classes, alpha, beta, gamma. And he's talking about this number h, alpha, beta, gamma. And he's exactly asking the same question we are. How many elements have the product equal to the identity? So I'm going to tell you a little bit later in the talk why this has anything to do with my project. But for now, I need to tell you what a character variety is. And before I tell you what a character variety is, I need to tell you the basic building block of a character variety. And I said this in my abstract, what the basic building block is, and that's what an algebraic group is. Now, an algebraic group is not a very standard object in undergraduate or even postgraduate courses. So I want to tell you just a little bit about them. As the name suggests, an algebraic group, it just has to be a group, but it has to be a group with a very special origin. It has to have an algebraic origin. In particular, we require that it's a group cut out by solutions to a polynomial equation. Okay? And there's a bit of a caveat here. I'm not telling you actually the full definition of an algebraic group because I don't want to tell you about algebraic geometry. But there's a caveat that I'm actually only defining the affine algebraic groups. If you want an example of an algebraic group that is not affine, you can look at the elliptic curves. They kind of break this definition, but you'll have to forgive me from lying to you. So moving on, I want to talk about some examples of an algebraic group. So what's the simplest polynomial we can think of? Well, we can just think of the constant zero polynomial. And what solves the constant zero polynomial? Well, it's everything in our field. And so the associated algebraic group here is just the underlying additive group of the field. Now you've seen the additive group of a field before, the underlying additive group. I'm just casting a different light on this group. It's actually an abstract. It's not just an abstract group, it's an algebraic group. We can bump it up a notch and we can talk about two variable polynomials. I'm going to talk about this one, the product xy minus 1. That's a two variable polynomial. And if we're looking at solutions to this polynomial, well, a solution has to be a pair A inverse in order to solve this polynomial. And we have to pick A to be an invertible element of our field. And this A inverse, that second entry, A inverse, is kind of hanging along for a ride. It's not really supposed to be there. It's there, but we can kind of forget about it. So we're really just looking at invertible elements of our field. And so the associated algebraic group here is just the underlying multiplicative group of the field. So that's the entire field without the zero element. So you've seen these groups before. I'm just casting a different light on this. We can bump this up one more notch. If you asked me on the street what my favorite polynomial was, I would say the following. This is actually the formula for the determinant of a matrix, AD minus BC. And so this tells us actually the group of matrices in SL2 is actually an algebraic group. So you've seen this group before, but it actually has a geometric origin precisely because the determinant is a polynomial. And this kind of begs the question, what about GL2? What about all invertible matrices? If you remember, that just means determinant is non-zero. But that equation, the determinant being non-zero, doesn't look like a polynomial because I have a not equals rather than an equals. And we can actually get around this. We can perform this trick. I actually spoiled it before. The trick is to add this extra t variable. And what is this t variable doing? If t was 0, then I actually could never solve this polynomial, because if t was 0, this would be the constant -1 polynomial, which has no solutions. But if t is non-zero, we can always solve this polynomial. AD minus BC is just forced to be the inverse of t. And so what is this t really doing? It's playing the role of the inverse of the determinant in disguise. And it's a little trick we do, and it actually gives us all of GL2. So you've seen all of these groups before, and I just wanted to cast a different light on them. Now, before I move on, do we have questions about any of these examples? Seems like we're experts on algebraic groups, so I'll just move on. I just want to talk about one more example. We're going to bump it up one more notch. And what do we do? Well, I'm just going to think about this matrix. It's this funny anti-diagonal matrix with ones and -1s on the anti-diagonal. And what can we do with it? Well, I can just look at the set of all matrices in GL4 that fix this funny Q matrix. And we call this group the symplectic group of 4x4 matrices. And you may have seen this group before, but I just wanted to tell you that actually it's an algebraic group. Why is it an algebraic group? This equation AQ A transpose equals Q, if you write A out, the matrix A, if you write out every entry A, B, C, D, E, F, G, and so on, and you multiplied that equation out and you equated entries, well, there's 16 entries, 4 squared. There's 16 entries, so you get 16 polynomials in 16 variables. Now, some of those polynomials are repeated, so you don't get quite as many, but you can see if you multiplied this out, you would be getting an algebraic group. So this is just a very compact way of writing many polynomials, and I did not want to write them out. It would not be good to look at them. So the examples I've been giving you so far, they're actually matrix groups. They're actually groups of matrices, and that's not a coincidence at all. There's a theorem that says all algebraic groups are subgroups of the general linear group. So they're all matrix groups in particular. Now, again, there's the caveat that I said the word affine before, and I don't want to carry it around. You'll have to forgive me for that. And so all of our favorite matrix groups are actually examples of algebraic groups. GLN, SLN, symplectic matrices, special orthogonal matrices, and so on. And there's actually a much deeper process happening in the background. If you've looked at representation theory or Lie theory and stuff like that, you may have seen the Dinkin diagrams, the famous Dinkin diagrams. And for every Dinkin diagram, there's many algebraic groups associated to it. And there are very precise procedures. Given a Dinkin diagram, how can you create algebraic groups? So there's a very deep story here that I do not have time to talk about. But just pick your favorite matrix group and that should serve you well. So now I'm ready to talk about the space I study being a character variety. And we build it in a very straightforward manner. All we do is we take a surface. So this is some two-dimensional surface living in R3. And I want it to have some genus holes and I want it to have some punctures. And what am I going to do with this surface? Well, I'm going to compute its fundamental group. So here I see pi1, that's the fundamental group of the surface. And we can see the genus holes in green and we can see the punctures in blue. So remember, this is a hollow torus. It's like the surface of a balloon. And I'm taking a pinprick. So imagine the balloon did not explode if I pricked it with a pin. I'm removing a single point. Those are the puncture holes in blue. But we can compute this fundamental group. It's not too hard to compute. It's just generated by a couple of generators, and it's subject to one relation. And it's subject to that relation on the bottom, you see. This product of commutators and these yi's, they have to be one. So I've written it in this funny numerator denominator notation, but that's all it is. It's a group generated by many variables subject to only one relation. And so now we're ready to define what the character variety is. We take this funny surface group, this fundamental group of a surface, and we take two more simple pieces of data. This is why we had to talk about algebraic groups. I need to take an algebraic group as well, and I take some conjugate classes in my algebraic group. And I take one conjugate class for every puncture on the surface. Now, maybe it's not clear why we're doing this. It's just a bit of bookkeeping that we have to do. And what do? Well, we look at the following space. We look at all homomorphisms from that fundamental group into my algebraic group. And we call this space the representation variety. Now, I'm saying the word variety. It's synonymous with the word space for the purposes of my talk. I do not want to talk about algebraic geometry. We call it the representation variety, but you could call it the representation space. And all I have is this funny condition. I need to send this yi generator to the conjugate class Ci. So this is the space that we form. Now, this begs the question, why is this even a space in the first place? It's a collection of functions. How is that a space? And I'll get to that in a moment. But if we think for a second, what if G were the general linear group? What if this algebraic group, G, were the general linear group? Well, if we've done representation theory, we would have seen a representation just is a homomorphism from a group to the general linear group. And so if G were GLN, we would be getting true representations of another group. So that's why we call this the representation variety. Now, keeping with that analogy, if you've done representation theory, you would have seen two representations are equivalent if they're conjugate by an element of the group G. And so we have an action on this space by conjugation. I'm not going to go into detail about that action, but it kind of picks out equivalent representations and it collapses them and it calls them the same thing. And that's what the character variety is. We take the quotient by this action. And so I kill all representations that are equivalent except for one. I take the space of inequivalent representations, and that's what we call the character variety. Now, there's a few questions here. What quotient am I taking? Well, you can just think of this as the space of orbits for now. But there's a deep story here with the GIT quotient and stat quotients, but I do not want to go into that at all. But you can ask me about that if you wish. So the question I alluded to before is, how is this a space? It's a set of functions. How is that a space? Why am I giving it the name space or variety? Well, this is a homomorphism on a finitely generated group. The generators are AI and BI and YI. So instead of thinking of my function as a function, I can think of it as a tuple of images of generators. Now, every image of every generator lies in the algebraic group G, and G is a space. I told you this algebraic group was a space itself. And so instead of thinking about a space of functions, I like to think about a space of points. This is how we give this set the structure of a variety or a space. And I understand this is very abstract. It took me about 2 years to get comfortable with this, so I want to do an example. Let's just do a concrete example so that we stay grounded. I'm going to pick the torus, that's genus 1, and I'm going to put 3 punctures in it. Well, what's the fundamental group? It's the group generated by 5 generators subject to one relation. And then what is that representation variety I told you about? Well, I identify it with the following space. It's just all quintuples in my algebraic group G, and subject to one relation. I require the commutator and these yi's. I require their product to be 1. And I require this yi matrix to live in the conjugate class. So I understand this is a lot to get your head around. But this is just a space of matrices, because I told you the algebraic group G is essentially a matrix group. So this is a space of matrices, and that equation on the bottom, the commutator of A and B and the yi's, that equation is coding many polynomials in many variables in disguise. So this is truly a space cut out by polynomials. So that begs the question, how do we study this space? Before I move on, I just want to take a moment to offer questions, if anyone has any questions about what I've just done. Okay, seems like we're all very comfortable. You know my topic better than I do. So that begs the question, how do I study this space? What does it mean to even study this space? Well, we go back, not quite back to the 19th century. We don't go back to the 1800s. We go back to the 20th century. And we look at a paper written by Andre Weil. He wrote this paper, I think, in the 1920s. And he made a very, very fundamental, non-obvious observation. At the time, he was interested in solutions to polynomial equations in finite fields. That was the title of his paper. And he noticed if you study the solution set to polynomial equations over finite fields, what you get tells you something about the space that you started with. And we're going to go through a concrete example of this. So this polynomial, it cuts out some space. And maybe you have a question about the dimension of this space, or its number of components, or its Euler characteristic. Andre Weil, he made a very non-obvious observation, and he said, you study the solutions to this equation in finite fields, and it will tell you about the space. It'll tell you about the topology and the geometry of your space. And you can see at the bottom, he's actually talking about the Riemann hypothesis. And this is a very deep story, going back to Riemann himself. But for now, I just need the moral of his paper. So what does he say? He says, say you have some space and it's defined by polynomials with integer coefficients. So our representation variety, our character variety, they're examples of this. You can think of spaces very easily. And we're going to do the example of the circle in a moment. The circle is defined by x squared plus y squared equals 1. That's a polynomial and it has integer coefficients. That's another example. And what does Andre Weil say? He says, morally, if you want to study your space, if if you want to study the topology and the geometry of your space, you should look at the number of solutions to that polynomial in finite fields. So that's what I mean by this XFP notation. We call this counting points over finite fields. And we're not interested in the exact solutions, we're just interested in the number. We're interested in the cardinality of this set. And Andre Weil says, he makes some very precise statements. But broadly, you can just think of this as, if I count this number, I start to understand the topology, the geometry, and the cohomology of our variety. Now, I'm not going to talk about cohomology that much, but that's what I mean by this H star notation. But we need more than just a moral, we need a theorem, and the theorem goes as follows. If I count the number of points over finite fields, and if that number itself is a polynomial, then it's a very, very important polynomial. It's called the E polynomial of the space. And this polynomial is very different to the polynomials that define your space. So the circle is defined by x squared plus y squared equals 1. But how are we getting a different polynomial? This is something you need to separate in your brain a bit. So what is the E polynomial? You probably have not heard of it. I hadn't heard of it until I started the project. Well, I'm not going to give you the definition because it would take ages to talk about, but it's some polynomial and its coefficients encode topological, geometric, and cohomological information. And what's this theorem saying? It's saying we can compute that polynomial for free if I can find the number of points over finite fields. So it does a lot of the heavy lifting for us. I can avoid the definition of E polynomials altogether. And so what do I get if I get the E polynomial? Well, the dimension of my space is actually going to be the degree of the polynomial. And another non-obvious piece of information, maybe the dimension is obvious to you, but the Euler characteristic might not. All we do is we evaluate the E polynomial at the point 1, and we get the Euler characteristic. And we can keep going. Maybe I don't know if my space is connected or not. Maybe that's a question I have. So the number of components of my space, is going to be the leading coefficient of my polynomial. And so that's what I mean by that funny pi naught notation. That just means the number of components of my space. Now I want to solidify these ideas with an example to set everything in our brains. I want to do the example of the circle. So that's what I was alluding to before. It's defined by a polynomial with integer coefficients. And Andre Weil says we should study the solutions to this equation in finite field. So we're going to start with the number 2. I look in the field F2 and I find 2 solutions. These are the coordinates 0, 1, and 1, 0. And I can bump this up a notch. I find a few more. I find 0, 2, and 2, 0. And of course, you could do this on a computer. You can go up to 5 and 7 and so on. And we get this evolution all the way up to F19 and so on. The key here is we're not interested in the exact location of these solutions. We're only interested in the number. And not only are we interested in the number, we're interested in the relationship with the prime P and that number of solutions. So you could put this on a computer and figure out exactly what's happening for any fixed prime. But a computer could not tell you the general behavior of this number. Or maybe it could if you asked ChatGPT. So what's happening here? Well, the general behavior is as follows. If you count points over finite fields, the number of solutions is basically P minus 1. And actually in those graphs I showed you before, there's actually counterexamples to this. This is not true for every prime P, but it's true enough. If your prime is one more than a multiple of 4, then this is actually definitely true. But for some other primes, it's actually not true. But it's true enough of the time. And I'm sweeping that piece of detail under the rug. You can trust me. The number of points over finite fields is P minus 1, and that's the E polynomial. And so I told you before, we can recover facts about the circle. So the well-known fact that the circle is dimension 1, I can get this from the polynomial. I read its degree. The Euler characteristic, I just evaluate this at 1, and I get 0. We know the circle is Euler characteristic 0 now. And if you weren't sure if the circle was connected, you can check the leading coefficient of this polynomial. And so I know now the circle is connected, it's dimension 1, and its Euler characteristic is 0. I see we have a question in the chat, I think. Is it close in the same kind of way? Like whenever it is wrong, is it always overestimating the number? It is actually always underestimating. It is always underestimating. If this equation is wrong, for example, it's wrong for the prime 2. You could see before there were two solutions. If the prime was 2, this formula says there should be one solution. But we saw actually there were two solutions. And if you knock it up a notch, you look at the prime 3. 3 minus 1 is 2, but we actually saw 4 solutions. This number is actually, it's always underestimating, but that's actually an irrelevant piece of information. It's kind of a coincidence that it's underestimating. Um, all you need to know is this is true enough of the time, and we can talk about that a bit later if you want. I just find the example of the circle a very motivating visual thing. Unfortunately, it's not literally true. This equation is not true all of the time. Okay, so this begs the question, how do I study my representation variety and my character variety? How do I count points on them? And what does it even mean to count points? Well, luckily, these spaces were built out of matrix groups. And so to count the number of solutions over finite fields of my representation variety, I just look at these matrix groups with mod p coefficients. So GL2FP, SL2FP, and so on. And so when I'm computing this number, I'm really asking how many matrices are there in this finite matrix group whose product equals 1. This funny expression is 1. And I require these yi matrices to lie in a specific conjugate class. So this is what it means to count points. We're really interested in this number. So I want to ground ourselves a little bit. Let's do the example that we had before, the genus 1 surface with 3 punctures. And so I'm really looking for all quintuples in a matrix group who satisfy this equation. Now we're getting back to the historical question I started the talk with. You might have been seeing it coalesce a little bit. So how do we evaluate this number? Well, Frobenius himself tells us how to do this. At the time, I don't think he actually knew this formula himself, but he essentially told us what the formula was. And the answer is as follows. The size of this set, it's basically the sum. We have a correction factor, there's the size of the group, but it's basically the sum. Now this is, we call this Frobenius's formula because it's very closely related to the problem we started with at the start of the talk. So I'm summing over these characters of a finite matrix group, and I'm summing up all of these funny expressions, these complex numbers. Some of these are integers, some of these are random complex numbers. There's a very intricate expression, and there's a lot of detail going on here, but I'm not going to be talking about the detail. All I wanted to point out is if we substitute G is 1 and R is 3, this formula is basically the formula we started with. So in evaluating this formula, I want to remind us that we actually want to evaluate this for every P. Not only do I want to know this number, I need to understand this number's interaction with the prime P. So if I fix a prime P, 2, 3, or 4, 5, 4 is not a prime, and I fix a matrix group, you can actually figure this out on a computer, no problem. If you fix all of the variables, this is a completely determined problem. But we're really interested in this interaction between the prime P and this number. And we want to show it's a polynomial relationship. That's the key I want to focus on. But there's a big elephant in the room, which is that sum, the sum over representations of a finite matrix group. That's a very, very intricate set. And so that's what I want to talk about. Now, I'm not going to be talking about representation theory exactly. I just want to talk about the history of the set. So the history of the set is as follows. We have a nice table in one of my favorite textbooks, written in 2020, and they detail the history of the representation theory of finite matrix groups. And it goes back to Frobenius himself in 1896. He essentially wrote down this set. So he was looking at representations of the finite matrix group PSL2 FP. And a little bit later, about a decade later, they managed to work out SL2 FP and GL2 FP. They understood their representations. Now, if you pick P, this
Hey
is actually
Bailey,
a very easy. Yeah?
hey Bailey,
Hello?
quick question. Can you hear me?
Yeah, I can hear you.
Just wondering, did Frobenius write down, like literally write down the character table for PSL2?
I think he wrote down the character table for alternating groups, which is isomorphic to this group, I
Right,
think.
okay.
So yeah, we're looking at um, representations of finite matrix groups. And you can see, I just want to point a few things out in this table. There's a very large gap between the GL2 entry and the GL3 entry. You can see 1907 by Jordan and Scher, and you can see 1951 by Steinberg. That's a 40-year gap. So it took 40 years to go from GL2 to GL3. And there's even a larger gap. If you look at SL2, that was 1907. That was sorted out in 1907. But if you look at SL3, it was sorted out in 1973. So that's a, what is that, 55-year gap? It's a very large gap. So this is a very, very tricky problem, even for fixed matrix groups. But the kind of state of the art on this topic is actually a paper published in the 70s, where they handled a lot of these groups all at once. And that paper was written by Pierre Deligne, a Fields Medal winner, and George Lustig, a member of the Royal Society. And they wrote a paper in the Annals about the representations of finite matrix groups, and they used the word reductive groups. So you can see there, they're talking about we're concerned with the representation theory of a finite matrix group GF. And the key to their paper is they deal with these funny representations called virtual representations, RT thetas. You might have heard of them. They're called Deligne-Lustig representations. And that was the key construction in their paper that allowed them to uniformly solve this problem for many matrix groups all at once. So I'm not going to be talking about exactly what happens there. So let's go back to character varieties. This is one of the last things I want to talk about. So what is the results about character varieties? Well, the first paper that really broke a lot of ground on this topic was written by 3 or maybe 4 authors, depending on how you count the appendix. It was a series of 2 papers in 2008 and 2011 by Tomáš Halzel, Emmanuel Letelier, Fernando Rodriguez Villegas, and Nicholas Katz. And I'm not going to talk about exactly what they did, but I wanted to point out a few things. In their abstracts, they say they calculate e-polynomials of character varieties coming from GLN. And they do this using the strategy I told you about, counting points over finite fields. And they looked at the characters of the finite matrix group GLNFP. And these are very deep papers and they touch on a lot of topics. They touch on combinatorics and Lie theory and cohomological topics. They're very deep papers, and I recommend at least a read of the paper on the right. It's a bit of a tour de force. There's a lot of deep combinatorial things happening in these papers. So what did they prove? Well, they just counted points on finite fields of a GLN character variety. That's all they did. Now that's a bit reductionist to say. It's not all they did, but that's all I want to talk about. And they computed points over finite fields, and they found that the number you get is a polynomial. And it's not at all obvious that it even should be a polynomial. It could be a crazy relationship between P and this number, but they were able to write down the polynomial. They were able to write down the expression. They found it was a polynomial. And so that must be the E polynomial. And that gave them a lot of topological, geometric, cohomological information about the space. In particular, they found the dimension, they found Euler characteristics, and they were able to prove that the character variety was connected because they were able to read off this information from the polynomial. And I want to stress they did this for general linear groups, GLN, and they did this for general shapes. So that surface I started with has a genus G and it's got punctures on it. They did this in full generality, but they only did it for the matrix group GLN. And they found something very striking. They found actually the coefficients of the polynomial they got was a palindrome. So if you order the polynomial in order of ascending degree and you read the coefficients, it reads backwards and forwards the same way. And this is not at all a coincidence. There's something very deep happening here cohomologically. If you've heard of Poincare duality, that says roughly the top cohomology and the bottom cohomology are the same. And so Poincare duality says there's a mirror image in cohomological information. And if you trust me when I say the E polynomial is capturing cohomological data, this is what we're seeing as well. We're seeing a mirror image in the coefficients of the polynomials. And this is not at all obvious. Character varieties do not satisfy the hypotheses of Poincare duality. So this actually should not happen, or at least it's surprising that it happens. So the next topic, the next paper on this topic, there's only really one paper on this topic other than that, and it was written by a student of Fernando Rodriguez Villegas, and he dealt with the symplectic group character varieties. So he bumped it up a notch. He looked at more exotic matrix groups, and he found much of the same information. He found points over finite fields, he got an expression, and he computed features of the polynomial. And he also found it was palindromic. And that brings us to our project. Well, we did the same thing at the University of Queensland, but we did not fix our matrix group. So we dealt with a very broad class of matrix groups. Precisely, we dealt with algebraic groups that are reductive and have a connected center. Now, I don't want to define what a reductive group is, but roughly, algebraic groups sometimes have a bad subgroup, and we just want to make sure this bad subgroup does not exist. That's all the reductive assumption is saying. And all of the examples of matrix groups I've showed you before are reductive. The general linear group, the symplectic group, special orthogonal groups, most matrix groups you think of hopefully are reductive. And then we also just ask that the center is connected, a very light topological condition. And we did the same thing. We did exactly more or less the same thing. We computed points over finite fields and we got a polynomial with a lot more work, depending on how you look at it. And so we found dimensions, Euler characteristics, and we also found a striking piece of information. We have a disconnected character variety in general. And we know exactly why it's disconnected now. Its disconnectedness comes down to whether or not the center of a certain other group is connected. And that certain other group is the Langlands dual group, G-check, that I've written. So if you learned about algebraic groups, you learn they often come in pairs. And we call them Langlands dual pairs. They have their own center, and you just check if that's connected. And we also found that the polynomial was palindromic. So the last thing I'll say is the following. You can enumerate this problem. You can put it on a computer for a fixed prime P. You could put this on a computer. For a fixed matrix group and for a fixed prime P, you can put it on a computer. But now that we have this theorem, we can actually figure out the E polynomial. If you fix your prime P, you will never find the E polynomial. But now we have this theorem, we can find E polynomials, and we can put it on a computer now, and we can actually ask a computer, what is the E polynomial? I'm hiding a lot of the detail. We have actually an expression for the E polynomial, and that can be put on a computer now. So that's what we've done in Julia. That skipped a lot of things. That's what we do on Julia. We wrote a package, character varieties. Now we can load matrix groups in Julia, and I can ask for the E polynomials of character varieties now. You see there that example G is 1 and R is 3. That's the torus with 3 punctures. So that's the E polynomial. And you can see the coefficients are palindromic, -5, -5, -2, -2, and so on. And the real thing to take home is we can do this for more or less any matrix group now. We can do this for special orthogonal groups, and we can do it for much more exotic groups now. Groups coming from G2 Dinkin diagrams, F4 Dinkin diagrams, and so on. And this was not able to be done before. And so going forward, the real thing I'm thinking about now is, what do these numbers mean? Is there a pattern here? We know some things about the numbers. I know the leading coefficients. I know what happens when you sum them up. I know they're palindromic, but what are they really saying? And so that is the end of my talk, and I've finished with a nice picture of some of the UQ group and some of our friends who worked on this project. So thank you for listening. Do we have any questions?